Look familiar? So you're sitting in your circuits class and you have just been exposed to Thevenin and Norton, but you're wondering, how is this going to be on the test? What can I do with this to solve my circuits problems? I'm about to share with you some tips and tricks I wish I knew when I was in circuits. They can save you a lot of headaches and pain and save your grade too. Thevenin and Norton is basically, you get something like this circuit right here. This is like your load, like this is receiving like voltage and current and power. And this here is a circuit that's delivering that. But this here actually has an equivalent circuit that can be simplified to something like this. You have your Thevenin equivalent and you have your Norton equivalent. V Thevenin, voltage Thevenin, resistance Thevenin, I Norton, and this is R Norton. And these here are the loads. A complex circuit can be replaced by a simplified circuit. And clearly we can see the obvious advantage. And here's that advantage. To construct such a circuit, we can just recall Thevenin is always VOC, voltage open circuit, is equal to short circuit current times R Thevenin. This is a very important idea. Here's our circuit, and let me clarify some stuff. V Thevenin is equal to V open circuit. I Norton is equal to I short circuit. R Thevenin is equal to V open circuit divided by I short circuit. Now, what we want to do is we want to find the Thevenin equivalent circuit of this. And with these concepts right here, we can easily do that. To do that, just redraw the circuit and disconnect the load. So here's our circuit with the load disconnected. And now I will clarify something. If you're wondering, oh, what is voltage open circuit? It's just this. That's it. It's just the voltage without the load. So how do we find that? Here's how I found that. So there's no current going through R3 or R4. So it's simply a voltage divider, voltage across R2. And here's what that would be. There is your voltage open circuit. Now you might be wondering, okay, that's good. But what about the short circuit? What's going on there? I'll tell you what's going on there. So let's redraw the circuit. So right here is what I'm talking about. If we replace the load with a short circuit and we wonder what's the current through there, it's just that current going through there without the load in is just I short circuit. And we want to find what that is. What we're going to do, so what we really need to do is find the voltage across these two resistors and then divide it by the resistance to find I short circuit. And here's how we do. So we have Req. R equivalent is equal to just R3 plus R4, and that's in parallel with R2. All we really need to do is that we just do a voltage divider concept. Req R1 plus Req times voltage source, and that is multiplied by the reciprocal of the resistance, R3 plus R4. So this here is the voltage across the two resistors, which is the same as the resistor voltage across this guy. So after we do that, we just divide it by the resistances, and there you go. We did it. Yes. We have voltage open circuit. We have current short circuit. Here's the next step. We can make an equivalent circuit. So we have this here. This is called our Norton equivalent circuit. So we have the I short circuit that we found, and we have Rn. So what is Rn? Here's Rn. R Norton is voltage open circuit divided by current short circuit. And current short circuit is also known as I Norton. This has an equivalent circuit as well, and that equivalent is this. So this here is our Thevenin circuit. From this relationship, we know that V open circuit is equal to I short circuit times Rn. And V open circuit is also known as V Thevenin. R Thevenin is equal to voltage open circuit divided by current short circuit. And that is the same as R Norton. They're the same. This is the simplified version, so to speak, of the more complex circuit. This is called Thevenin equivalent circuit. I think of these things as like tools to solve a problem, like a hammer or a screwdriver or wire cutters. So I want to show you another tool that is a very useful tool. This is a very good tool. I'm about to show you. Our second concept tip that we want to remember very well is called the look back method. Don't forget the look back method. Circuits problems are really like searching for information that's given to you, if you make a habit of solving circuits a certain way, a certain sequence that you feel secure with, you'll run into a problem where you can't solve it because they want you to do it with a different way. And let me show you. Let me show you. We need to find the Thevenin circuit for this. I'll show you how to do it. So first we want Thevenin. So to get Thevenin, what do? How do we get Thevenin? What in the world do? Here's what we do. We just remove the load and find V open circuit. And here's what that would be. All right, so with this guy, we have voltage open circuit. Here's an equivalent circuit. So now to get voltage open circuit, all we really need is like basically, say we call this, node A and we call this node B. And to get that, we just need, voltage at node A minus the voltage at node B is equal to voltage of open circuit. So that's how we can do it. So how do we do that? Is that we have our reference right here. So this would just be, we call this node C. And so we just need to find the voltage, from the ground to node C and from node C to node A. And then we can find the voltage at A. And the voltage at B, we can find the voltage at B through another method. To find the voltage at C, it's just, think of KCL. KCL, I5 is this. It's equal to I2 plus I1. And we have that. And we know the voltage at node C is just equal to I5 times R5. And that is actually just 12 volts. The voltage at A, well, to find the voltage at A, we know that the voltage of A minus C is equal to I1 times R2 because we have the current source and we have the resistance and they're in series. So it's like we know the current going through this resistor. It's just from that source. And that's just 2 volts. The voltage at A is just 14 volts. Boom, 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 boom. Now to find B, the voltage at B, we just do node analysis. From inspection, we can write this equation. And if we solve it, the voltage at B is equal to negative 6.667 volts. VA minus VB is equal to the voltage open circuit, which is equal to Thevenin, which is equal to about 20.667 volts. Now, to get I short circuit, we just gotta short it. So with this, if we short it, now, how do we get it? What's the plan? What's the approach? Well, this isn't easy. We could find the current through R2. Then we could do KCL at A. Then we could get the current through R3 and R4. We could also do node analysis. And, that's a lot of steps. A lot of chances for something to go wrong, and a lot of time. So what do we do about this? We can use the look back method. So I redrew the circuit. So we opened the load, and then we were measuring the resistance, the equivalent resistance from the load. Plus and minus, we're measuring the equivalent resistances. Now, before we can measure the equivalent resistance, we have to turn off all the sources. So for current sources, we open them. We have 2 current sources, we open them. And for a voltage source, we just short it. And then there we go. Boom, 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 boom. And the equivalent resistance is just R2 plus R5 plus the parallel of R3 and R4. REQ is just 10,000 kilo ohms. And that is also our Thevenin. Our I Norton is equal to V Thevenin over R Thevenin, and that's equal to 2.06 milliamps. When the pressure is on, if you can find a way that's like quick, we don't want to kid around. All right, for trick number 3, what is the source circuit? Sometimes we call it the source network. So what is the source circuit and what is the load? We don't have to be constricted to a source that's always on the left side and a load that's always on the right side. We can think of it in other ways. So I call this tip abstract the load and source. Abstract the load and source. This is an RC circuit, and don't worry, you'll get here. You'll know what's what. But here's the deal. We want to know what the time constant is, and that's just this. RC, R times C, the resistance times the capacitance is just a time constant. So if you think that that the time constant therefore is just, it's just R2 times C1, that's wrong. R2 times C1, think about this. So for an RC circuits, we know that, here's the deal. For this circuit, we know the time constant is RC. So to solve this, to get the time constant for this circuit, we just need to, find the Thevenin equivalent. So we get this guy, it becomes this circuit. Here is our load, and here is our source circuit Thevenin equivalent. The green is our source circuit, and the blue is our load circuit. Because you can look at the original circuit, and there's the load circuit. And the source circuit is this guy. So there you go. You can just see it like this. You have your loads and we have our source circuits. Here's our Thevenin. It's just, voltage divider, because, you remove the load and then you just a voltage divider for the open circuit. And for our Thevenin, it's just the look back method. And if you do that, this is short. You short this and you just have R1 in parallel with R2. So now we can clearly see the utility for this way of thinking. And our time constant would just be R Thevenin times C1. So the professor may try to throw you off and do something like this to put the fear of God into you, during an exam. And with this way of this tool, the tool that I'm showing you is this way of thinking of the load in this network. It should alleviate any kind of stress like that. So time for trick number 4. That would be, lots of comprehensive problems have Thevenin built in. So this circuit right here is an inverting op-amp configuration. And what that means is that the voltage output is just the minus R2 over R1 times Vn. And that's it. Basically, an op-amp is scaling up the input voltage. And that's it. So what do you have? You something like this. Whoa! All right. It's okay. Look at the circuit. The circuit is like what do you do with the circuit? Oh my gosh, what do you do? Here's what you do. It's easy. Did you already forget tip number 3? We abstract the load and the source circuit. This right here is like the source circuit, and this op-amp configuration right here is like the load. So I can just let me just redraw the circuit then. So here's the guy. Here it is. Here's the circuit. So the R load, we can just think of this as this circuit. You have a voltage divider, and the look back method, what we just went over, and there's your equivalent. So right here is the circuit again, and this is the same. And if we just saw the inverting op-amp configuration, and so the voltage output is just this. That's it, because we know what VT is. And if we want it in terms of the source, like this guy right here, if you want it in terms of the source, it's just this. It's just that. VT is just that, because VT is right there, and that's it. Your professor may write problems that are somewhat comprehensive and require you to remember topics that you learned earlier in circuits. And you may have to use Thevenin when you are not explicitly told you can. Thevenin and Norton are in your toolbox, and don't forget that. Thevenin and Norton are in your circuits toolbox. Don't forget that. Oh, what crazy, incomprehensible circuit is he going to show us next? Oh, what's it going to be? So here's the tip. Here's the final tip. Ooh, the tip. Make a crib sheet of your tools. If you are waiting until the day before the exam to make a crib sheet, you're gonna have a bad time. Start right now. Right now. If the professor wants you to turn in a crib sheet, make a copy. Just scan it. Thevenin and Norton are never going away. These guys right here are impedances. So we want the ratio output to the input. So how do we do that? What we do is Thevenin and Norton. This guy is our source. This guy is our load. Remember, the capacitor we chose, even though we want the inductor, the voltage across the inductor, for this intermediate step, we're treating the capacitor as our load. So we're not mixing in with this guy because we are just keeping our analysis on just the current source and the resistor. So the impedances act just like resistances for Laplace circuits. So the way we find the output is just a voltage divider circuit. So here is here's the ratio. That R comes from right here. This is how we do it with Thevenin and Norton to solve for a Laplace circuit. So think of the circuits course as like a subject that uses a toolbox to solve problems. And here are your tools. This razor could be like your mesh analysis. And this wrench could be like your node analysis. And this level could be something like your KCL or maybe your KVL or whatever. You know, fix something or do something, you need your tools. You need a good toolbox. So you come to a point to where within reason, you can pick whichever tool you need to solve the problem. You know, maybe mesh or node analysis could both be used. You know, one's better for certain applications than another. And it's your job to find out quickly which one would be easier to use. In that look back circuit, obviously, you know, like instead of doing all this stuff, it's just so much easier to use the look back method. And sometimes you can't use the look back method if you have like dependent sources in it. Like look back method won't work. Like that's the takeaway that I would like you to have. And if you need some more help, here's my video on mesh analysis if you need some help with that. Thank you for watching. Good night. Sleep tight. Don't let the bed bugs bite. Good night.